Hello, everyone. Welcome to my talk. Thank you for being here, for choosing to open your conference with me. Today, I'm going to try and give you a good mental image of some security measures that are useful in embedded systems, and when they are useful and when maybe they're not the best fit for your use case. A few words about me. My name's Olivier. I am a security engineer at Bootlin. So we're a consulting company. We do development consulting around embedded Linux, and we also do training. My colleague Maxime just has a new network training out. We have a strong open source focus. That's why we're here in significant numbers. And we work around bootloaders, and we have a lot of build within Yocto integration experience. I'm contribute to open source because I think it's good, and I don't think anybody here is gonna disagree with me. And Bootlin is in a few places, but mostly in 2 cities in France, and I'm in Lyon, so in the southeast. Let's talk about embedded systems security. So security has been an ever more present theme here as well in this conference. And I think there's several reasons for this, but it's become so strong of a theme that it's like lawmakers have caught on, and they've decided, hey, we need to do something about this, and we need to make sure that people sort of raise the floor. That's really what they're worried about. They're worried about like due diligence and sort of making at least the lowest amount of effort towards security. So this is what, for instance, the Cybersecurity Resilience Act is about, the CRA. I'm sure you've heard about it. It's been discussed last year quite a bit, and it's going to be discussed this year as well, significantly. But there are other aspects of this. One big one is the reputational risk. It's not a good look today to put out a system that is completely insecure and it gets pwned like immediately. And this is a big reason for bigger security teams, more security effort. But also security is now part of the feature set that customers want. So customers are asking for security and they are choosing products based on this. And security has made it into marketing. So, yay. The problem with this is that it leads to the main sort of criterion being, I want the system to be secure. Like, this is really, hey, I want a secure system. And that's great in theory because you have secure or non-secure. That's sort of a binary state. But theory isn't practice. And in real life, security is more like a gradient. It's more of a scale. And really, when we try to make a system secure, what we try to do is raise the bar that an adversary or an attacker has to meet in order to do what they want on the system. So thinking in terms of it's either secure or not secure is of limited help when you're trying to make your system better, essentially. The reason, part of the reason why you need to have a discussion around what level of security you want is that it doesn't come for cheap. It's definitely not free. And there's several aspects about it. For like security, you have to think about it. You have to analyze what you write. You have to take care to design things in a secure way. That just takes time. Like it takes time, it takes brain power, it takes people. Sometimes it means you're going to have dedicated hardware. There's a talk today about TPMs. That's an example. It can mean your system is taking more time booting because it's checking the integrity of the software, because it's decrypting stuff. There's another talk about this during the conference. I'm not sure it's today. And it makes your system more complex. Systems are already complicated, but usually adding a security layer is going to add something that you have to have in mind when you're thinking about your system, be it a barrier that you have to approach in a specific way, or something that you might not be able to do anymore. So this is why going for max security is not necessarily the right thing. And that might be a bit hard to hear for product owners or things like this. But fortunately, going for minimum security is most likely the wrong option for the reasons that I mentioned before. So really what we want to know is, hey, where should I decide to place my security barrier, like my security level, essentially? So one tool that we have to think about it is threat modeling. And threat modeling is essentially saying, hey, what is the stuff that I want to protect on my system, and who am I expecting to try and get at it? And there's another thing in here is, what can I expect people to enforce? Some security measures will make it more difficult for users to use your system, and ultimately it's up to you whether you want to do that or not. And as I mentioned here, like, only some of this is technical. So it's not a purely technical, like, put your engineers on it and they'll make your system secure, because some of those decisions are like product owner decisions, right? The adversaries you expect, well, it depends on marketing, at least partially. What you can expect of your users, same thing. It depends on your target audience. So ideally, this would happen at the design phase when you're deciding, hey, this is what my system's going to be. But life isn't perfect. This is a significant effort, a threat model, because you have to think about sort of all of the aspects of your system. And obviously, the complexity of your threat model is going to scale with the complexity of your system. But I would argue that even a very simple threat model is helpful in discussions about what you should be doing for your system and how you should be implementing things, even if it's a simplistic one. And I think when you're designing your system, you always have a threat model. If you haven't sort of thought about it, it's just going to be a very, very straightforward, simple one that you're going to apply to sort of any system. Sort of like, oh, there's bad guys, and they want to scan my SSH ports, something like this. What you care about is your assets here. They can be sort of very different depending on your system and depending on what you care about. Customer data or user data is usually pretty high in there, but in a lot of cases, intellectual property is also a big thing. And crypto material is just a way to safeguard the rest of your system, right? And then your threat model should take into account the various levels of privileges, because that's what you're going to want to isolate from each other. And then what you really should care about is your adversaries. It's who you expect to be trying to take a shot at your system. It's going to be a very different story if you expect a 12-year-old or a 15-year-old who's bored and studying computer science to sort of take a shot at your system and try and look inside, or if you're expecting, I don't know, like government agencies to be looking at it. And that's going to warrant very different levels of scrutiny and security measures. So let's talk about those. I have a few that I think are the ones that come up the most that I would like to go through, and to give you an idea of when I think they're useful or applicable, and how to think about them in terms of threat model and your system. Essentially, the security measures, there's just a blocker between your adversaries and either a privilege level that they shouldn't have, or your assets. And what you want to prevent is transitions from one to the other. So the first one I would like to discuss is file system encryption. So file system encryption is rather simple. It's Linux. Well, in most cases on embedded systems, it's going to be Linux, essentially giving you a file system that is never resident on disk at rest unencrypted. And the kernel is going to make it as straightforward as it can for you to just use your files as if they were plain text on your disk. You shouldn't see a difference except a slight performance hit. Of course, if you have encryption, you have a key, and this is sort of the main problem here. And the key is usually either derived from a given password, this is sort of what happens on your laptop, right? Or it's going to be stored somewhere, possibly in a header, and it's going to be decrypted at runtime. And the question is where to store the key. And this is, again, where secure elements come into play. And again, there's a talk about TPMs today. This is a nice diagram that was presented here last year of the Linux storage stack by Werner Fischer from Thomas Krenn. This is the part that we care about. This is where this is implemented. I'm sorry that this is a bit small, but somewhere in here is the encrypt, and that's the part of the Linux kernel that is going to do this for us, the device mapper. So what is file system encryption good for? It's good for somebody picking up your system, opening it up, and reading directly from the hardware. That's what it. So this is sometimes called the evil maid attack, because it's like spy movies. The person who's cleaning your hotel room, sort of grabbing your stuff and opening it up and reading, like dumping it, spy style. And it's not going to prevent essentially anything else. Like, this is really about physical access to your data, because it's only going to be encrypted at rest, right? So it's not going to prevent live access to it. So what does it cost? Well, as I mentioned before, there's some performance. You have to implement it. Mostly, that's going to be a rather small cost here. The real problem is going to be the keys. That's going to be the significant challenge that you have to think about and that you have to solve. And there's a bunch of questions here. Do you want one key for all of your devices, meaning it gets dumped once and that's over? Do you want families of devices, or do you want one key per device? How do you provision them? Who's the custodian is going to be a big question, because you could put that in the hands of your user base, but then you're going to have to have a rather educated user base. And of course, the problem is data loss. That's what you're really trying to prevent. And I've lost data because it was encrypted. So this is a real risk. So that's the big problem. And if you put this in the hands of your users, then you're not going to be able to help if they mismanage their keys. But if you decide to do it yourself, then you're liable in some way for, oops, I don't have your key anymore. Here's a simple threat model for what this could look like. So essentially you have your remote adversaries here. The way that they're going to get at your system is the network. And if they get RC on your system, then they're indistinguishable from the good access. So essentially there's no protection here, right? And you have your local adversaries, and they're the people who are going to be, well, they're the evil maid, right? They're the people sort of opening your system and trying to get at it from the physical side of things. This is what encryption does for you, right here. It does not do anything for this, right? That's not its job. That's what I mentioned before. This is the part that you're trying to mitigate. And if I get RC on your system, then, well, I still have access to the data because that's what the data is here for. Really, this is more what the threat model looks like after you implement encryption. The reason for this is cold boot attacks. Essentially, people have figured out that devices don't store data only on the disk. There's a bunch of other memories, like caches and RAMs and all kinds of other places that systems store data. And that means that if I get at your system while it's running, I can take your RAM, put it in liquid nitrogen, and that's going to prevent the data from dissipating and from erasing itself too quickly. And then I can potentially dump it, recover the encryption key that is somewhere resident in there. It's not going to be necessarily super easy. I have to know what I'm looking for. And then if I have physical access, I dump the data, and now I have the key, the encrypted data, and it should be fairly straightforward to get at the actual data. So we went from this to this. So there's still a path to the unencrypted data. But what I would like to really draw attention to is that these guys are not the same as these guys, right? And the conditions for them to get at your data are much more stringent now. Like, they need a lot of access to your stuff for a long time. They need liquid nitrogen. They need to know that this is possible. They need to know how to do it. It's not the same people, most likely. So a big part of these guys are not going to be able to get your data in. And so that's what you get. You don't get, oh, nobody can get my data from the physical side of things, because that's very difficult to achieve. But you get way fewer people are able to. And that's going to mitigate a lot of opportunities, and that actually makes your system safer, even though there's still a path. So when is that a good use case? Essentially, I mean, it's when you're putting your stuff out there and you're not having somebody look at it all the time, because otherwise you're just going to catch the person opening the system and trying to take stuff apart, hopefully. Another place where it's useful is when you don't actually trust your users. And that's not that uncommon. One big example of this is gaming consoles. Gaming console manufacturers tend to think that their users might want to compromise their system to do all sorts of things and run all sorts of software that shouldn't be run on there. And so this is one possible use case. So you don't have to only encrypt data. You can encrypt code, of course. And this is also one typical use case for this. So this goes a bit into security to obscurity. And this is usually a bad design principle. But I would argue that it's only bad if you're only relying on obscurity for your security. It can be viewed as a delay tactic, essentially, because it's just going to make it harder for people to understand how your things work, and therefore to be able to compromise your system. If your system is not storing user data or significant sensitive IP, it might not be super worth it, because you're going to complicate your provisioning, you're going to complicate the boot of your system and the overall thinking of how your system works for low gain. So you might want to not do that. So typically, small routers, I'm not sure it's worth it. If your system is being surveilled constantly, like the answer to this physical security problem is not necessarily encryption. It can be just surveillance or a physical way to prevent people from getting access. As long as you have an answer, essentially, if you have an answer somewhere in your threat model saying, oh, we're just going to check that people are not taking apart my ATM, then you can say, okay, then encryption is not worth it. And if you're trying to make a very small device, you might not want to take the performance hit if you don't have crypto accelerators. The next big thing, the next big security measure, I think, is secure boot. So secure boot is a way for all of the software on your platform to authenticate itself from one component to the next. You have to trust something at the start. Like you cannot manufacture trust from ex nihilo. So you have a root of trust. Usually it's one or multiple hashes of crypto material, so of a key, and you put it in write one's software because you don't want to be able to overwrite it. That would defeat the purpose. One typical example for this is fuses. And it has to go all the way up to the kernel. So everybody has to participate. And the first element in this is the boot ROM from the vendor. But you then have to have all bootloader stages participating in this. It will mitigate the same type of attack. So essentially, I grab your hardware and I put my software on it that I would like it to run, and then I just boot it up and it works. But another thing that will mitigate is the software actually modifying itself and changing what is on here so that it will persist. Like they will essentially, if your system reboots, then the compromise will still be here. This is if all of this targets kernel, essentially, or bootloader software. This is not for userland. What it will not mitigate is the software getting pwned, essentially. So if somebody found an RCE or a remote code execution or like a buffer overflow somewhere, they can still exploit it. And this is not going to help at all. And it's also not meant to verify the userland, so that's also not going to help for userland. So here's a diagram of how this works. You have a read-only memory here where the boot ROM is stored, and that's your encode. So that's a normal boot, and then you load your bootloader and your kernel from whatever boot medium, and this is typically an attacker finding, some buffer overflow, some command injection in one of your apps, and gaining user level access like this. And then either they have a local privilege escalation to gain kernel, or they have a kernel RCE. They tend to be more rare these days, but and you have your root file system here containing your userland, right? So this is typically a problem. So this is your userland sort of modifying itself on your root file system, or even managing to modify the bootloader or the kernel. And this is a typical persistence vector. This is, hey, I've gained access, but I would like to still have access when you reboot, and I would like to not have to do all of this work again of triggering an RCE and getting my exploit detected by your IDS or whatever. And this is the physical compromise. So I just open your system, find your rootfs, change it, or your boot medium here with your bootloader and your kernel. I change it to something that suits me better, and then when you boot, well, I just automatically gain code execution, right? And I've compromised your system. So this is what sort of the global threat model, still a simple one, but looks like, with all of the threats that I've described. And here's what secure boot helps with, right? This part. This, unfortunately, is still here. And the way that you mitigate this, there's a lot of other mitigations, but essentially it's this is where you're looking that your stuff is patched, helps looking that you're hardening your apps, things like this, that your kernel is the latest. So this is a lot of hygiene. And this is what we're mitigating. These guys, they don't have access anymore. They still have userland access, but they don't get kernel. So one problem here is that we still can change the root file system and get userland code execution, and that's already not good. So the answer to this is verification of the root file system. So the implementation in Linux is dm-verity. That's still in the same part of the Linux storage stack schema that I showed you before. Essentially, it's great. We've verified up to the kernel that we're running what we expected to run when we made the system. How do we make sure that userland is still fine? And the problem here is that userland is huge, at least compared to the kernel. For most systems, it is big. And so the idea and what is implemented in Linux is that we're going to build a hash tree for the file system, block by block, right? We'll store it somewhere else, and we're going to hash the hashes together. Like the hashes at one level are going to be hashed together, and they're going to give hashes of a upper level all the way to one hash. That's going to be the root of the tree. And this you can sign if you want to add some security. And when the kernel is starting to, this is not going to happen at boot because this would be a huge performance penalty. So we're not going to verify the entire file system at boot. But when the kernel starts to access data on the disk, it will essentially load up the hash that is in the tree and verify it up to a hash that it has already verified, so up to a node that it knows it has already verified, and then it was going to walk back down to check all of the hashes down of that hash. So if I change a file on the file system, when the kernel is going to try to access it, it's going to hash it, and if it finds that it's different in the hash tree, that's already not going to be great, but I can change the hash tree, right? Because it's just on a different device. So if I can change the file system, I can also change the hash tree. And so if I have changed the hash tree, this is going to propagate all the way to the root, and the root hash is going to be different. And this is the part, this is why you potentially sign your root hash. It's so that if I change the root hash, you should catch me. And then if I change anything on the file system, Verity is going to essentially throw an error, like the file system is going to refuse to load the file. So here we get mitigation of persistence of userland code. This is the problem that we had before. And if there's a secure root properly implemented, then we also don't get userland code execution anymore if I have physical access, right? The problem is this is implemented by the kernel, so anything that has kernel level privileges will be able to defeat dm-verity. But this is what we get. This is no longer possible. So we had these two with secure root, this one with rootfs verification. So we've eliminated this side of the threat model. This one, well, it's still here because that's not what we were looking at with this. Some things we then need to be looked at when implementing dm-verity or rootfs verification is that security is really depending on the root hash, right? That's the linchpin because you're not protecting the hash tree, but you're verifying this every time. If I can create collisions, then of course, if your hash function is insecure, then that also defeats the scheme, which is why MD5 is not amazing. There's a publication called PUC or GTFO that has two different files with the same MD5 hash, for instance. It's a neat trick. So it's now possible to generate two files with the same MD5 hash, so rather easily. And this is implemented by the kernel. So if your kernel is compromised, it's also not going to work. And the kernel command line, this is how the hash can be passed. This is an option. And so the kernel command line is also going to be something you need to verify. So if you're implementing secure boot, these are the things that you're going to have to include in the verification of the kernel level components. Like the root hash is going to have to be included in this. Because otherwise, when I want to modify the root file system, I'll just also modify the root hash, and that's it. It doesn't fully require a read-only file system, but your file system is either going to be read-only or write once, because once you've written it, essentially the kernel is going to refuse to read it again. So really, you want a read-only file system. Otherwise, your device is not going to work anymore. So that's the main cost of rootfs verification, is making a read-only file system, because that's not exactly what the operating system has in mind necessarily. There are rootfs file systems with great support in Linux, but you have to make sure that your system is going to work with this. And most likely what it's going to mean is having other file systems that rewrite from which you should not execute stuff, right? If you make other file systems rewrite and then you have a capability to just be like, oh, I'm going to get some scripts from this place, well, you've defeated the purpose. So this is, again, a bit of design to ensure that your system is going to help rootfs verification. One other cost of this is updates, because this is going to work with secure boot, hopefully. So you can implement this without secure boot, and it's not nonsensical. It does add value in the sense that now if I only have userland execution and I don't have local privilege escalation to get kernel, I don't have root privileges, I can persist, right? Because usually I'm not going to get access to the boot medium. And it's going to be harder to get kernel execution. So this can be useful if you don't want to do all of the secure boot stuff, but mostly it makes sense in the context of secure boot. The problem is you cannot do rootfs updates only, because if you change your rootfs, that means your hash tree is different, that means your root hash is different, and your root hash should be verified before, right? And so the signature that you're using to authenticate your kernel is different, and so you have to propagate, because secure boot is a chain, you sort of have to propagate the update of the chain. And if you have AB updates, then you need to if the root file systems are different, then you need to make sure that you can keep track of which that the bootloader can keep track of which root file system goes with which root hash, right? So it does make updates a bit more complicated. Rootfs verification itself is great for preventing persistence, and so for network connected systems, that's a lot of them, but really, I think this is a big one. There are a lot of small devices connected to the internet that are routinely targeted for botnet enrollment, meaning, oh, I'm just going to take a random exploit that I know works on a lot of devices. It's been small office routers quite a bit. Like MikroTik had a big problem with this at some point. I think TP-Link tends to be a big target as well. And the other one is IP cameras, just because there's even less scrutiny on this. And the first thing people do is install a backdoor so that they don't have to compromise the thing over and over again. And if you're implementing secure boot, you should really implement root file system verification, because otherwise that means, oh, you've done the work up to the kernel and then you stopped. But that's probably not where your system is going to stop. So it's not great if you have partial updates. So if you have a package distribution, it's not amazing, because at this point your root file system is changed, and now you have to essentially update the entire chain. And if you have stored user actions, this is the example I was giving with the script, well, you might as well be okay with the root file system being modified, because essentially you're just giving another option for persistence. So in that case, it's probably not the best. The last one I would like to talk about is secure enclaves. So secure enclaves are just an isolated unit of computation. Like, it's just on your system, there's some hardware that says, hey, this is even more secure than the kernel, essentially. The main technology for this in embedded devices that you might run into is on ARM, it's trust zone. And essentially you have two worlds now. You have secure world and non-secure world. So they're also split into trusted and rich. And essentially what this means is that to get access to the secure world, you need a further privilege escalation, right? You have privilege escalation from user land to kernel land, and now if you want to have access to this, then you need another one. This is very much defense in depth, because at this point, this is useful in the case of somebody getting root access to your system. It's like your last line of defense when somebody has gotten significant access. Essentially, what you do is you put your secrets only in the secure world, and you only use them in the secure world, and you give the output of that to the normal world, to an interface. There's an API for this in the case of Opti, for instance. And so that's how the normal world gets the output of this and doesn't get access to the actual data in there. So here's a representation of this. Essentially what happens is that your boot ROM is in secure world, so the secure world here, normal world here. Your boot ROM is here, bootloader, and then there's a transition happening. The kernel gets loaded. And if the kernel wants something from your secure world here, it has to go to an API, right? And it cannot just get direct access to the hardware, just like userland cannot get direct access through the hardware. In this case, it's a specific part of the hardware. The rest is still accessible to your kernel. The problem here is that the secure world is going to be a less nice environment for you to write code in, because it wouldn't make sense to just take Linux and put it in secure world, because then your attack surface is the same, right? And that's not what you want. This needs collaboration from hardware. This is a hardware security measure, just like the exception levels or the isolation between kernel and userland is a hardware security measure. So it needs collaboration from the hardware. It needs to have tagged, these places, they're for secure world or they're for normal world. And unfortunately, secure world can be insecure as well. We have some examples here. And what that means is that you need to pay more attention to your secure world than you do to your normal world. So this is more work. Like, it's a significant added cost in both design, in development, and ultimately in maintenance. If you just put stuff in secure world and develop them the same way, like if you put a bunch of stuff in secure world without any security analysis, then it's probably not worth it. The physical access here is going to be a different level of physical access than before. Like getting stuff out here is going to be significantly more difficult, but it's going to be, side channel attacks or people actually extracting chips. This is going to be rather difficult in high-level adversaries. What is not going to be mitigated by secure enclaves is use of the data or of the secrets, because ultimately you want your system to use them, but it's going to mitigate exfiltration. So that's good, for instance, for licenses. That's typically one use case, or for biometrics. Essentially, you have either global crypto secrets that you want to protect on your systems, or you want to tie it to a physical machine, so in the case of licensing, or you handle small sensitive information that you can handle entirely in secure world. If you don't trust your users, that's also usually a big part of it. So this is useful for voting machines because they handle very small sensitive information, or for biometrics. This is where it's largely used in phones, for instance. But it's going to be, again, a significant cost. And this is why if your user base is not very security aware, then that's going to be a lot of cost on you for not a lot of rewards necessarily. This is not necessarily users here. It can be people who design things for your systems. In the case of licensing, for instance, the users are not really the people that you increase the security for, but the corporate owners are. Okay, so this was my talk. I hope I gave you a better idea of what these security measures are for and what they try to mitigate and what they really don't, and in which cases you might want to consider them, and in which cases it's probably not worth your time. Thank you. If you have any questions. This, yeah.
What kind of overhead is there for using something like the file system level? Like very expensive.
What kind? Sorry, what overhead is it for file system verification? Yeah, no, it's definitely usable. The main like the performance is not going to be a problem. The question is more: do you want to take the time to implement it? And if you implement root file system verification, do you also want then to have secure boot to have the complete chain? Knowing that then it's going to make it's going to have ripple effects, right? It's going to make your updates harder. It's going to make some of your product lifecycle more complicated. But the performance is not the main problem, I would say. Yep.
Yeah, about dm-verity.
Mm-hmm.
Did you say that it only works with read-only file system? Or?
Yes. So does dm-verity only work with read-only file systems? Technically, no, because technically you can have dm-verity for not read-only file system. The problem is when you modify your file system, the hash is going to change for this file system now. And if you don't change the root hash that the kernel is verifying against, then the next time it's going to try to access the file that you changed, it's going to do this verification right up the chain and get a different root hash. And when it does that, it's going to refuse to load your file.
How do you verify that root hash is something embedded in the kernel admin time?
Yeah, so essentially you can, so there's two ways, but this is why I mentioned the kernel command line. You can pass it to the question was how do you pass this root hash and how do you verify it? Essentially you can pass it on the command line of the kernel. And so this is why if you implement secure boot and dm-verity, but you don't include the root hash in the verification of your kernel, right, from the bootloader, then you haven't really implemented dm-verity. Because I can just change the root hash and the scheme is useless. Yep.
Can you give an example how to reasonably store keys or certificates without using a TPM or a trust zone?
Depends what you mean. So the question is, can you give an example of how to reasonably store a certificate or a key without using a TPM or trust zone? It depends on what you call reasonably, really. Then my next thing would be a smart card, but it's not super helpful because essentially it's just a different secure element from a TPM, but then you have to have a smart card reader, and I'm not sure that that's what you want. And that depends on your security threat model. Essentially, you can decide that you're going to have a wrapping key that users don't know. You can decide that you're going to leave that to the user and that they're going to have to input your password, right, every time, and that you're going to only store the key encrypted and decrypt it using a key generated from the password at runtime. That's an option, but it puts significant pressure on your users because now, if it's the boot key, for instance, this is what happens on the laptop, but that means every time you boot your system, somebody's going to have to come in, type in a password for your system to be able to boot, and that's not necessarily what you want because that means your system cannot boot by itself, right?
You talked about dm-verity,
Mm-hmm.
and it could slow down the boot process if the rootfs is accessed during boot.
Yes.
So the kernel will end up accessing the rootfs, mount it, and load the init or system B.
Mm-hmm.
So at that time, do we get a performance hit?
A small one, yeah. But what I was saying is this is why the kernel is not verifying the entire root file system at boot because then the performance cost would be huge. So it's only doing it when it's loading the file, and it's only going to do it for this file, right? It's going to essentially walk up the tree either to the root hash or if it's already walked part of the tree, it's only going to walk the part that it hasn't walked already, and then it's going to go up there and then walk back down. And so, yeah, if you need to load init, then you're going to have to verify your init. That's the point, right?
The granularity is of 5.
No, the granularity is a data block, so that depends on your file system.
So the more the data blocks, the longer it takes.
Yes. Yeah. I think that's all the time we have for the next presenter to be able to set up and for everybody to be able to join the next talk. So thank you everyone for coming.